Before looking at specific configurations for our 555 timer, let's take a look at the block diagram and get a better understanding of how it operates. So as we can see here, we're looking at a basic block diagram. If you want to see what the actual circuit looks like broken down to the transistor level, you can look on page 1102 in Niemann. So just glancing at this, we can see we have several components. We have these two comparators. And so let me label some things a little more clearly. We have C1, which is a comparator, C2, which is also a comparator. We have this RS flip-flop. We have a buffer on the output stage. Notice that both of these have these little circles. And so in that case, these little circles are indicating inverters. So if we have a high signal, it's switching to low as it goes through that. And then down here, from this output of the RS flip-flop, we also have a connection to a discharge transistor. And so we're going to go through how each of these components works together in a little bit, but I just want to label these first of all. So notice I have several of these pins sort of around the perimeter of this drawing, accompanied by a number in purple in parentheses. And so you notice that, including this one down here at the bottom, they don't all quite fit on the same screen. But they're numbered 1 through 8, and so of course what these are the pin labels for the actual IC. So our IC is going to have 8 pins, and so kind of keep that in the back of your mind as we're talking through this. If you're like me, you might need a quick refresher for your RS flip-flop if you've not dealt with it in a while. So here's a truth table for our RS flip-flop. We can see for our case when S and R are both 0, we have no change in our output state. For the case of S0R1, we're performing reset, so our Q goes low and our Q naught is high. For S1R0, we're setting it, so our Q is 1 and our Q naught is low. And then for both S and R high, we have an undefined state. Okay, so let's kind of step through this block diagram and see if we can't figure out what exactly is going on. So we're going to start by looking at this comparator C1, and this is called our threshold comparator. So threshold comparator, C1 above in our block diagram. And so what we can note by looking at this threshold comparator, so we're looking here, is we can see, of course, we have two inputs. One of these inputs, our inverting input, is connected directly here. And so what is this connected to? Well, if we sort of focus just on this vertical piece for a moment, we notice that we have just a really simple voltage divider. We have our input voltage V+, and then we have 3 5K ohm resistors in series. So one of the inputs to our comparator C1, our threshold comparator, is going to be coming off of that voltage divider network. We can see that the other input, so I sort of have it jumping over here indicating that it's not connected there, is connected to our threshold pin, which is pin 6. So that's of course why we're calling this our threshold comparator. So that V minus value, so V minus is what I'm calling the input voltage at the inverting terminal of our threshold comparator, is set by that voltage divider. So it's set by our voltage divider, and so that voltage divider network, like we saw, it's all internal to the 555 timer, which is R3, R4, and R5, and each of those was 5K ohms. So what that means then is that our V minus is fixed at 2/3 of whatever our power supply voltage is, V+. Okay, so what that means then is we're comparing some value which is 2/3 of V+ here to some input value which we're calling threshold for now. So let me get rid of those and let's come back down here. And what we're saying then is when the input, which I'm calling my threshold pin, so pin 6, exceeds this V minus value. So our V minus value, which is 2/3 of our V plus, what happens is the output of that comparator is going to go high. So the output of C1 goes high. And so that's just sort of our basic comparator operation. If you have questions about that, definitely let me know and we can review. And so what that means then is we can see the output of C1 is our R. So right here we see our output of C1 is R. So coming down here to our truth table, we see if we have R is 1, then we're going to have our reset state. So what that means is that the output from our flip-flop is going to go high, because up here note that our output is labeled as Q naught. And for R equals 1, we have Q naught is 1. So coming back here, we say our output for comparator C1 goes high, which means that our RS flip-flop output goes high. So RS flip-flop output is high. Okay, so what's that going to do? Well, if we have a high signal here at the output, what we can see is we're essentially turning on this discharge transistor down here, and that's going to be connected to an external capacitor at this discharge terminal. So we'll come back to that when we look at specific configurations and see how that's going to come back and affect our input and our timing. So basically what we're saying though is that this output of our flip-flop being high turns on our discharge transistor. And so as the name implies, that's going to allow a capacitor to discharge through this transistor. So it turns on discharge transistor, and what that's going to do is it allows an external timing capacitor to discharge to ground. And so again, we'll come back to specific configurations later, but this external capacitor is going to be connected to pin 7, and so when that transistor is off, it doesn't have anywhere to discharge, but we're essentially treating this Q14 like a switch, so as soon as that's on, then this capacitor has a path to ground in order to discharge. Okay, so basically we've seen our condition for the threshold, our input over here, that needs to happen in order to turn that discharge on. So one thing we've sort of glossed over is the fact that we also have this connection here at pin 5 called our control voltage. And so for the configurations we have, we're going to not really be using that, but what we can do is we can use that in general to control that reference level a little more if we want to. So our pin 5 allows for external control of that reference. And so that's, of course, the reference level for our threshold comparator C1. So as I said, typically we're not going to use it. So what we're going to do is we're going to bypass it with a capacitor to ground. So when not in use, bypass to ground with a 0.01 microfarad or a 10 nanofarad, same thing, capacitor. And what that does is that's going to improve our noise immunity. So I'm just going to say, well, I'll go ahead and write out improve noise immunity. So keep in mind as we're wiring our circuits, I don't believe I have it explicitly shown in the notes. It probably is in the lab, but if we're not using that pin 5, we want to bypass it to ground to keep from having a lot of noise. Okay, so that covers sort of our comparator 1. So now what we want to focus on is our comparator 2. So our comparator 2, we're going to call our trigger comparator. So I'll scroll up in a little and we'll see why that is. So our trigger comparator, which is C2. So coming back up here to our diagram, we're now looking at this bottom comparator C2. And so of course we see one of the inputs is the trigger. So that's why we're calling it our trigger comparator. So what we can see is, again, we have a fixed input based on this voltage divider. Now it's to our non-inverting terminal. And then this external input from our trigger, again, it's hopping over, so it's not connected there, is connected to our inverting terminal. So let's see what that means in terms of operation. So again, just like with our previous comparator, we have one of these fixed. So our V plus of C2 is set by that same voltage divider network. So the same one that we talked about for our C1, it's just now we're taking it at a different point. So what that means is now our V plus, which I'm calling the voltage at our non-inverting terminal of C2, is equal to only 1/3 of V superscript plus, so our input voltage. So if you be careful with notation here, if I have the subscript that I'm using as the input at our non-inverting terminal, and the superscript is our power. Okay, so now we have it fixed at 1/3 because we're sort of one step further down that voltage divider. So what's happening then? So we're comparing, so we have this value fixed at 1/3 of our overall supply voltage, and we're comparing that fixed value to our input from our trigger. So let's see what happens as that value is changing at the trigger input. So what we can say is if our trigger level, so when our trigger level, so this is like our input, and again this is going to be pin 2 as we just saw above, when it goes below this value, so when it goes below our V plus, V sub plus, which is 1/3 of V superscript plus, then what happens is the output of C2 is going to go high. So the output of C2 goes high. And so what we can see then is our output of C2 is our S input to our flip-flop. So we come down here and we say, well, what happens when our S is equal to 1? Well, that's going to give us a Q naught of 0. So we can see again, we have Q naught as the output here. So that means we're going to have a low signal connected to the base of that transistor. Okay, so coming back down here, we can say then this being high means that our RS flip-flop output is low. So RS flip-flop output is low, or let me say goes low. And so what that means is that that discharge transistor is going to be turned off. So if we scroll back up here, basically what we can see is now if we have some external capacitor which is connected to our discharge pin, when this transistor is turned off, it no longer has a path to ground, it can't discharge, so it begins charging up. And so sort of getting ahead of ourselves a little bit, we can say, well, if we use the voltage across that capacitor and connect it back in some way to our trigger and threshold values, then as it charges up, it's going to be meeting some criteria for these comparators to switch their output states, which then is going to turn on a discharge capacitor, discharges the capacitor. Once it gets low enough, our transistor turns off, and then we are again charging up our capacitor. So that's sort of a look into sort of where we're kind of going in terms of basic idea of control here. So the one other pin that we want to talk about that we haven't really addressed yet, well, two we haven't really addressed explicitly, our output. Of course, we're going to see later that's just going to be giving us a square wave output, and as I've shown in previous videos, but also this reset pin, pin 4 on the top of our flip-flop. So let's talk about that and what we typically want to have that set at. So this is called our external reset for our flip-flop. And so as we saw above, that is labeled as pin 4. And so this external reset is essentially going to override all other signals for our flip-flop. So it overrides all other inputs, so inputs coming from our two comparators, And what it does is essentially we're saying this is going to initiate a new timing cycle. And for our pin 4, to initiate a reset, it has to be less than a certain value. And so that value is 0.4 volts. So pin 4 must be less than 0.4 volts to initiate reset. And so what that means for us then, when we're actually wiring these circuits, is if we're not using reset, we want to connect it to our power supply. So we're not using reset. We want to connect pin 4 to V+. And so what that does is, by doing that, we can avoid accidental resets. So that covers sort of the explanation of the basic block diagram for our 555 timer. So now we have a good understanding of what's going on inside our 555 timer. And in the next videos, what we're going to look at is our monostable and our astable configurations. And we're going to see how we can connect external components between all of these pins and get a certain operation.